Hello, I'm here to talk to you about something called improper integrals. Oh, so improper. Oh my goodness, who knew we were being proper this whole time? But we have been. So there are a couple warm-up questions at the start of the notes for this lesson, and I would like you to try each of them, first by hand, and then checking using FN on your calculator, and compare and contrast your answers. And I am leading you down a rosy path, so understand that that is true, but just give it your best shot, and then we'll come back and take a look. Okay, so pause the video. All right, try them yourself, try with the calculator. Okay, I invite you to pause the video if you think you might need to look at this screen for a little bit, but I'm just going to kind of talk through it. And question 1, you can see I anti-differentiated, not a very hard antiderivative, and plugged in my bounds, and I got an answer of 2. And the calculator also gave me something pretty close to 2, and I think that's probably just built-in rounding error. So I'm kind of thinking, okay, 2 seems like it's the answer. I got it 2 different ways. In question 2, I did all this work and, anti-differentiated. It looks like a nice little du over u integral. And I got natural log of 2, but my calculator says there's an error. So being a kind of visual person, what I went to then was to think about what each of these functions looks like. So this function, when I graphed it, has a curve like this, but then I noticed there's also this asymptote, a vertical asymptote at 1. And if I look at the equation, I can see why that would be, because at 1, if I try to evaluate the function, I get 1 divided by 0. Yeah, that's not a thing, guys, okay? So there's a vertical asymptote here. And 1, in addition to being an asymptote, was also one of my bounds. This does seem like a problem of some sort. And then if you take a look at number 2, you might say, well, my bounds are fine. 0 and 3, I can evaluate this function both at 0 and at 3. However, between 0 and 3, this function also has a problem at 1. It has the same problem, actually, right? You have an asymptote located at x equals 1. And so this is what we mean by improper. Improper integrals occur because we're defining things that we normally define in a certain way as not the way we usually define them, right? So you might not have realized before that there are certain requirements to the kinds of functions that we have been working with and the kinds of bounds that we've been working with when we've been looking at definite integrals. So just as a reminder of vocabulary, I have in your notes these sentences that I just want us to complete. So when we have something like this, okay, we have an integral, it has a little a and a little b on it, right, a couple of numbers. That is what's called a definite integral. That should not be news, and it is going to produce a numerical answer, right, because it can represent something like area underneath this curve from this starting point to this ending point, right, things like that. If we have an integral that doesn't have bounds written on it, that's what's called an indefinite integral. That's where we find an antiderivative. And that's where we have our plus a constant, because it's actually a family of antiderivatives. Okay, now until this point, we've had sort of these conditions that have been, stated, but not really important because we didn't deal with the other case. So we have always been integrating. Every problem we've given you has had a continuous function, right? Which would mean no things like vertical asymptotes going down, okay? And we've also only had bounds that were finite. That is going to change as of today, but when those conditions change, you then have something that is called an improper integral, okay? Discontinuous or infinity in a bound, okay? An improper integral that actually has a value, because some of them do, okay? An improper integral that actually has an answer is said to converge to that number. So it might remind you of series, which shouldn't be shocking because aren't integrals limits of series, limit summations? Yeah. So an improper integral that actually adds up to a finite value converges to that value. And an improper integral that has no limit is said to diverge. Okay? So there are some boxes that clearly I just snipped off the interwebs in your notes, and it talks about how to split things up. So if one or both of your bounds are infinity, and I'm going to say this as an infinity, meaning positive or negative infinity, then you basically rewrite things using limits. So you can see in the first case, if infinity is at the top, you do a little rewrite, and I usually use B for the top bound and A for the lower bound. And so you would just rewrite it as a limit as B goes to infinity and put a B where that infinity was. I tried to color code there in yellow to help you out. For number 2, I have a negative infinity at the bottom of my integration. So I'm going to rewrite that lower bound using the letter A and say A is approaching negative infinity. Now, if you happen to have an infinity on both ends, you're basically just going to split it at some place in the middle. Make sure it's not at an asymptote. So pick your favorite number, say your favorite number is 3, then the C that is stated here would be a 3, and then to each of these, you would apply what's up above. This would be the negative infinity case, this would be the positive infinity case, okay? Here, in this other box, we have things about vertical asymptotes. Okay, so you can have a vertical asymptote in between the bounds, or you can have a vertical asymptote located at one of the bounds. And that's what each of these is about, okay? So each of those cases is about having either a discontinuity at the edge, right? So at B, at A, or somewhere in between A and B, okay? And then it shows you how to set up each one. Rather than read those in general, I would like to do a slew of examples with you. This example is not written out in your notes. This is just to see. Okay, so just take a look at it with me. So if I have the function 1 over x, and I am integrating from 0 to 1, well, the problem value here is 0. Okay, so the problem is this lower bound. And so I guess I contradict myself here because I said I usually use an A here. Let's just make that an A because that's what I would usually do. I usually use, A down here and B up here. But you don't have to. You could use anything you wanted as long as it wasn't the x or whatever your independent variable is. You can use an n, what have you, okay? This looks sloppy. So we're going to have A approach 0, and then from the right. So the direction thing, sometimes people have a hard time with, but I'm just going to show here on my picture. The interval we're speaking of is 0 to 1, and the problem value is here. You always are going to express the limit as approaching the problem value from inside the interval. It makes no sense to be looking at it coming from this direction because this isn't even what the problem is about, right? That has nothing to do with anything. That's like I ask you, what's your favorite meal? And you tell me my favorite color is purple. Like it has nothing to do with anything, okay? So we set this up as a limit, and then we go ahead and do our calculus, okay? So we anti-differentiate. We have our bounds, and again, I guess I should really just commit to having this be an A. All right, we have our bounds, and then we're going to do fundamental theorem and plug in our bounds. And then we're going to go back to the beginning of our calculus life and take a limit. Okay, and that limit doesn't equal anything. There is no finite value. And so if the limit does not exist, if the limit is infinite, then the improper integral diverges. Okay? So that's an example just to look at. These next few examples, what I think would be good is for us to walk through a couple together, and then I'm going to have you do some where you pause and come back, right? You know what I mean? Like just to try some on your own. Okay, so this first guy has an infinity as the upper bound. And so I need to make a replacement of this upper bound. So I'm going to rewrite it. I'm going to use the letter B for up there. And say B is approaching infinity, so that replaces everything I need to replace. The rest of the question is as it is. Then I'll do the calculus. The limit part I don't need to deal with right away. Anti-differentiate, have my bounds, use fundamental theorem, plug in my bounds. Remember that the natural log of 1 is 0. I was a little sloppy here with not writing down all the things. Okay, and so I have natural log of something that's getting bigger, 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 and it too will get bigger, bigger, bigger. And so this is divergent. Okay, our next one, same beginning strategy. This top bound is the infinity. So I'm going to rewrite that as a limit as b approaches infinity. I'm going to anti-differentiate, just carry that limit along. I have my bounds. Apply fundamental theorem. Okay, now as b gets larger, 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 this part is going to get smaller, smaller, smaller. And so overall, this limit is 1. So this one was convergent. Now you might wonder, two things here that look pretty alike. This one diverges, this one converges. You might remember the idea of speed being a thing when we talked about series, and we talked about how you have to have something get small enough fast enough in order for adding up all of the different components to actually add to something finite. This one does not get small enough fast enough in order to equal something finite. But because this x squared in the denominator makes this function, as compared to the first one, get smaller faster, and it indeed is fast enough for the sum to be something finite. That's kind of cool to think about, okay? This next one has a different issue, because I don't even see an infinity. This is actually the dangerous kind of problem, because in this one, you know, like when you see an infinity in the bound, it's like, hello, rah, 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 rah. This is an improper integral. That was a British siren, in case you didn't know. Okay, but here it's not so obvious. There's no infinity sign like slapping you in the face. You have to just, because it looks just like a regular definite integral, but you have to be cognizant of the fact that that 0 is a problem child. We can't be dividing by 0. Okay, so I'm going to rewrite this. I'm going to put an a in the bottom. I'm going to keep the top bound. I'm going to let a equal 0. I need to think about direction on this. So if I'm thinking about the interval from 0 to 1, and here is my problem value, I need to be approaching my problem value from inside the interval that the bounds define. So I would be approaching it from inside the interval. So that means I'm approaching from the right. Okay, if you're like me, I have a little bit of a left-right issue. Drawing that picture really helps me. If that's you too, I recommend it. Okay? If you don't have that issue, you're like, why don't you know right and left? It's a lifetime of teaching. I'm just saying, like when I'm in the classroom, I point left when I say right, and it's confused my brain. You know, 22, 23 years of this. Okay. You understand why I say the wrong word, right? It's because I'm facing students and I point. Okay, think about it. All right, so here we are. We have our antiderivative. We're going to substitute in, and then we'll think about our limit. Okay, and so I have as a approaches 0 from the right. Okay, so if I'm getting smaller here, then this part is going to get bigger, bigger, bigger. And something going to infinity, subtract 1 from it, still going to infinity, my friends. So this diverges. Okay, I think we should probably do some where you set them up yourself. Okay, so let me think for a sec. Yes, I think it will be perfect for you to try 4 and 5 and come back in a second or two and see if you did them right, okay? Please try them yourself. We'll do number 6 together because that's a little more spicy. Okay, try 4 and 5. Okay, so we had one that diverges, that's problem 4, and one that converges, that's problem 5. Problem 4, you needed to rewrite the upper bound because of the infinity. Problem 5, you needed to adjust because the lower bound causes the function to be undefined. Okay, so hopefully that's okay. If it's not, pause the video and take a look at my work versus yours. Okay, let's proceed on. Question number 6 is a great question because it helps us review something we recently learned. Not only does this question have an improper integral issue, because of that infinity. It also has an integrand, which we could do with integration by parts. We need to do with integration by parts. Okay, so I'm going to make my little tabular integration by parts table over here, and I'm going to have x minus 1, and then my derivative of that would be 1, and my derivative of that would be 0. And the piece that I get to integrate is the other part, which is e to the negative x. And when I anti-differentiate that, I pick up a negative. And when I anti-differentiate that, I pick up another negative, which would make this positive. And then I love calculus, I hate calculus. I love calculus, I hate calculus. And then we take our diagonals. And that's all we need to take because the next one would have the 0. Okay, so set that aside for a second. Let's first do our rewrite. So we're going to have our limit as b goes to infinity, replace this top part with a b. Then we're going to take our antiderivative off of that table on the side that we just worked out, right? Because that's where the antiderivative is already figured out. So my antiderivative there, let's read our diagonals. I'd have a negative x minus 1, so negative parentheses x minus 1 times e to the negative x minus, and then my next, oh, I just pointed at the wrong thing. I pointed at the wrong thing there. The negative is from here. I apologize. So a negative from here is this negative. I'm sorry. Okay, and then this next part, we would have negative e to the negative x. Okay, and then my bounds, I'm going to scratch this out because that's in my way. Bad planning of my slides. Okay, and then we'll substitute in our bounds and think about our limit. So substituting in our bounds. Doing math in my head. Okay, so that's substituting in the b. Substituting in the 0. That'd be 1. And substituting in the 0 is 1. Okay, so that substituting stuff I did not really like show my work, but I promise you I'm just plugging in b and plugging in 1. And then we're taking a limit as b goes to infinity. Okay, well this part, easy, that's 0. And then I'm going to think about the rest of this. Well, as b gets bigger, these pieces are going to grow much faster than the constant or the polynomial function that is in the top. So all of this is going to go to 0. Converges to 0. Okay? Question number 7. I'm going to give you a little nudge at the start and then have you work. So question 7 has infinity at both bounds and infinity. And so I mentioned before you could pick some intermediate value, right? Something in between like 3 and split it up so that you'd have to rewrite one piece that goes from negative infinity to say 3 and then rewrite the other piece that goes from 3 to infinity. But in this case, I would recommend using symmetry. You have an even function. This function is symmetric across the y-axis. So split it there. Say, okay, I'm going to go from 0, the line of symmetry, out to infinity, and then I'm going to double it. Okay? So here's my initial step. I would like you to finish this one, and then I'd like you to look ahead at number 8 and tell yourself what the issue is. Okay, before you come back and hear from me what the issue is. Okay, let's take a look at how you did. So hopefully you recognized, because this is one of my favorite antiderivatives, that this is arctan. Okay, so you would have arctan and then substitute in your bounds. And then something I hope you know about arctangent is what it looks like. It looks like this. Okay, because if you think about what tangent looks like, arctan is a restricted chunk of that, just one of the branches of tangent, but reflected over the diagonal line y equals x to make it an inverse, okay? And if you think about where tangent's asymptotes are, then we know where the horizontal asymptotes of arctan are. This line is at pi over 2. This line is at negative pi over 2, because this comes from tangent. That's where tangent's asymptotes would be, just going the other direction. So as b gets bigger, as we go further and further to the right here, this arctan function gets closer and closer to pi over 2. So this limits pi over 2. this limit's 0, and 2 times pi over 2 is just pi. I think this is my favorite question of the whole set. I'm just putting it out there. Okay, question number 8. Do you know what the issue is? Did you think about it? Because when you just glance at it, it looks fine, right? Just do an antiderivative. However, if you think about it, there's this vertical asymptote situation at 1. Okay, so you're going to have to split this up at the 1. You'll have a 0 to 1 piece and a 1 to 3 piece. So I want you to again pause and try to do the whole problem. Now that we've identified the issues at 1, you need to split it into 2 parts, 0 to 1 and 1 to 3, and then each of those is going to be a limit problem. Okay, try to set it up and finish it and come back to check. Okay, so let's take a look. We should have rewritten it. Now, this work you can see I stole from the interwebs, so it doesn't use the A and the B the same way that I personally do, but the idea is still there, right? On the 0 to 1 part, you have to replace the top bound. On the 1 to 3 part, you have to replace the bottom bound. The antiderivative should be straightforward. It's just power rule, not even a complicated U substitution. Then you substitute in, let's just look at this at one line at a time. Then you substitute in, this is where we left off, substitute in B and 0 and 3, and you might have used a C or an A. And then there are pieces that go to 0, and then the parts that remain are actually what this one converges to. It does converge to a finite value. It must be getting, the terms of it, if you think of it like a series, must be getting small enough fast enough. Okay? Now, question 9 is actually a preview for our next unit. I'm very excited about this next unit. It's all the rest of the stuff about series. So in this problem, P is understood to be a constant. So some examples of things that this might be would be like 1 over x to the 3, or 1 over x to the first, right? So different things that P could equal, all right? So we're doing this in general though, okay? So we're going to take a look at this and see what happens to anything that's in this form if our upper bound is infinite. So first, we could rewrite 1 over x to the p as x to the negative p. Then we would rewrite this so that our upper bound is represented by some other notation with a limit. Then I am just going to apply my antiderivatives, right? So this is a power rule situation. So the exponent goes up by 1, I divide by that new exponent. Then I'm going to use fundamental theorem. So here you do need to remember which letters represent what. So the P is some number, it's a constant. That is not what I'm substituting in for. I am substituting in the B and the 1 in place of my variable, and my variable is the X. Now, in terms of thinking about what happens, there's actually going to be 2 cases, and the cases depend upon the size of P. So we want to think about if P is less than or equal to 1 versus if P is greater than 1, because that's a tipping point in what happens in terms of the limit. Let's just take a look. Okay, so if P is less than or equal to 1, then that numerator on the first part is going to get bigger and bigger, and therefore you will have divergence. However, if P is bigger than 1, then B will have a negative exponent, and therefore you're going to 0, and therefore convergent. Now, I encourage you, I don't anticipate, right? We've talked about this in class. There's some things that you just get immediately, and I would expect you to get them fully right off the bat. This is not one of them, okay? So I would encourage you to go back and just study this question some more, and if you don't get it fully in this unit, that's okay. You will get it. This is something called a P-series, and it's also something called an integral test, okay? So it is previewing something from the next unit. If you can grasp more, if you can grasp any part of it right now, that's great. And if you don't, let's just stick with the questions that we've been doing, okay? Now, at the start of this video, we looked at 2 questions, and we had answers for both of them, sort of. Okay, now that we know more math, we know that that first question has a problem at 1, and that problem at 1 should be represented by rewriting it as a limit and then doing our antiderivative. So our antiderivative here would, I'm sorry, I already have an antiderivative. My antiderivative would just be power rule based. I have my bounds. I substitute in. That's going to be a 1 when I subtract. That's going to be a minus 1. And so if I look at this part's going to go to 0, and this part's going to be 2. So that one happened to work out, even if I blew past that discontinuity. So that was lucky, but we can't always count on the luck getting us through. There are plenty of times when I blow past an asymptote and it's going to be a problem. Okay, this particular one happened to be okay. All right, now the next one, by hand, we got natural log of 2. By calculator, we got an error message. So that's of interest, okay? If you work this one out further, it ends up being a pretty big mess, okay? Let's take a look at how that plays out. This is what we would have, rewriting the bounds that are problematic, right? We already replaced with a B and an A. And then we'd anti-differentiate and we'd have our bounds. So here we are, substituting in. And I know that natural log of 1 is 0. That's one of my favorite facts. And over here, I could use a log property to make that a little more compact. But the thing is, when you get to this step, you basically have an infinity minus infinity situation, right? Because if I think about coming toward 1 from the left, then I have natural log of something that's approaching 0. Natural log at 0 has a vertical asymptote. And the curve, my graph of natural log, is this one. So this is like negative infinity, and this is adding positive infinity. And infinities don't work the way that numbers do. It's not like 5 minus 5. This is some infinite amount minus some other infinite amount. And there are different sizes or cardinalities, they call it, of infinity. So we really don't know what this is. This is a problem that I'm going to just tantalize you with. I hope that you take a class called analysis and find out more things that were derived by the mathematician Cauchy, and you will then understand what happens with this one. It is indeed something that we would just say, it's infinity minus infinity, that's our result. We don't really have something. So our calculator was right in giving us an error message here. Okay, we just don't know based on only calculus. We need more than calculus. So never forget, there is more math even past calculus. And we'll leave it on that note. Thanks.